the probability density function. So the probability density function, which can be a single variable or a multivariable function, is basically a function that takes in a bunch of parameters and it tells you the probability of certain combinations of those parameters. So if, let's say, like you had 2 coins and you're like, what's the probability I get 1 head? It'll map to some point. I have 10 coins. What's the probability I get 3 heads, 7 tails? It'll map to another point. So this probability density, I mean, obviously this is a very simple example, a discrete example, because they're discrete values and it's not continuous. Very simple example, but obviously, as I said, it can get a lot more complicated. So the idea is you have these variables and you have this function that represents the probability. Now, why is it so important and what does it have to do with integrals? Because a very important property of probability density functions, and again, this appears a lot in statistics, and I'm in statistics, and Parker always hates that. Parker always hates that.
This guy's a nerd.
For some reason. I don't know why you hate statistics. It's amazing. But anyway, so it comes up a lot in statistics, and it also comes up a lot in quantum mechanics, right? So a very interesting thing about the probability density function is that the total area is 1, which makes sense. Because the sum of all possible probabilities should be 1, right? Like this is 20%, 30%, 40%. Like they should all add up to 100%, which is 1. So that kind of makes intuitive sense. But what does that mean? That area is basically the integral, right? So if I want to know probabilities of certain events happening, I would have to integrate over certain variables.
And now we've actually seen recently, and also not so recently, applications of this probability density function. For example, in quantum mechanics, obviously, there's for example, the position probability density. You're asking the question, what is the probability that your electron is sitting between these 2 distances from the nucleus, for example. And an interesting thing about that is you realize that the probability for an electron to be at 1 distance is 0, because you're integrating over 1 single point, right? And the area under a single point is obviously 0.
I mean, it's not 0. It just doesn't make any sense. It's not exactly.
It is 0. It is 0.
Is it 0 or no? Because I thought that it's just undefined.
This is actually the fundamental theorem part 2 that we skipped. Is that if you do have a definite integral that's being integrated between 2 bounds, you just plug in the 2 bounds, you do final minus initial of that antiderivative. And so if you're integrating over a single point, you're integrating, let's say, from 0 to 0. So it's just
f of something minus.
You're going to just plug in f of 0 minus f of 0.
Okay, I guess I didn't think about it. Yeah,
and so the answer is actually just 0.
You're right. I guess that's the way. Yeah.
Another application is that we saw this in thermodynamics while talking about Maxwell speed distribution of, for example, particles in an ideal gas. It's this like bell curve kind of shape that you get. And yeah, that's interesting also in the same way, because the probability that you find an oxygen particle moving at a single speed is 0. You have to be looking at intervals of speeds. You can actually get very small with your interval if you want to be quite specific, but obviously should we talk about uncertainty or
I don't know if we need to get into uncertainty because that doesn't have
no, that's
not necessarily fine. I think that would be going the extra mile, but I did want to add something like when you were talking about like probability in quantum mechanics, because and I think we have spoken about this before, one of the most fundamental things in quantum mechanics, like mathematical features about quantum mechanics, is the wave function, right? The quantum wave function, which basically describes the state of all the particles in a particular system. And by itself, it means squat. It means absolutely nothing. But when you square this guy, you get the probability density distribution. And again, that is again where integrals become very, very helpful. If you're trying to find the probability of certain events, of certain states, of this particle, of this system to be in certain states, to be in mixtures of certain states, all of this rises from integral calculus, and it assists a lot of the math behind quantum mechanics.